Hello, everyone. Thank you for attending in this lecture, Elliptic Cryptography. One of the other background that we needed to understand before discussion about growth 16. Okay, so let me start here. Yeah, so the general formula of one of the main categories of elliptic cryptography formulas is this: y to the power of 2 equals to x to the power of 3 plus ax plus b. So based on the different value of a and b, so the form of the curve would be different. So there are some other categories with different formula for elliptic curves, but this category is one of the most well-known in cryptography, and it is used so much in this branch of cryptography. Okay, so we want to see different form of curve with changing the value of a and b. So for instance, first we want to replace the value of a by -10 and the value of b by -9. And then so the form of elliptic curve would be in this form. So we have two disjoint figure that are generating the curve. So when we change the value of a and b, replace the value of a by 1 and the value of b by 9, so then the curve would be this one. Now we want to switch and use our website and see how we can change the figure with different values of a and b. Okay, so let me go back and then into website here. Okay, so in the ZKP part and growth 16, you see ECC, which stands for elliptic curve cryptography. And here you can define your curve by changing the value of A and B. So, and then you can see the curve here, which is this draw. So we can change the value of A like 3, and then the value of B like -4. And so this is the curve here. And then you can also make change the value of here the range to see the figure in a bigger range, right? So like maybe 50, and then maybe you want to change the value again, and then the other form of curve here. Okay, so now we want to start to talk about the next discussion in elliptic cryptography, which is point addition on the curve. So this is the curve that we will use for our discussion and computation when you replace the value of A by 1 and the value of B by 9. So this is our curve. All of the computation for the growth would be executed on this curve. So we want to work and discuss different concepts in elliptic cryptography on this curve, but the concept would be general and we can have it for other curves also. Okay, the first one is point addition. So we want to see how two different points on a curve could be added to each other. So for instance, we have a point here like P. So this is point P, and these are the X and Y coordination for the P. So the X coordinate is 2 and the Y coordinate is 4.36. And the other point is Q, and these are the coordinates for the point Q. And this was for point P. So here we want to define the addition of 2 points on the curve. So in general mathematics, we didn't already discuss addition of 2 points on a curve. It doesn't have any meaning. But here, later you will see how this addition allows in cryptography. Okay, to compute the addition of 2 points on a curve, you need to draw a line that is passing through the 2 points, P and Q, right? So this is this purple dotted line. This is the line that is passing through the 2 points. So then this line will intersect the main curve in a point, right? Which is here. So this is the intersection between the line and the curve. Now you need to reflect the intersection points over the x-axis, and then you will reach into a point that is the addition of 2 points P and Q, right? So this is a very simple method to compute the addition of 2 points. So other than the figure and draw the line, we have some formula that allows us to compute the addition. The formula first compute the slope of this line first. So the slope of this line is computed by this formula. The y coordinate of point Q minus y coordinate of point P over the x coordinate of point Q and x coordinate of point P. So here the y coordinate of point Q is this one, right? So this is this one, and the y coordinate of point P, so this is this one, over the x coordinate of P, which is this one, and the x coordinate of P, which is this one, right? So if you compute this division, so then the slope of line would be 0.68. So then the x value, the x coordinate of the point R usually is called the addition of 2 point P and Q. P plus Q is called R. So the x coordinate of this line, this point, is slope to the power of 2 minus x of P minus x of Q. And by replacing these values and then compute this computation, you will see the x coordinate of the point P plus Q or point R equals to minus 1.54. The y coordinate of this point also is the formula is the slope multiplied by x P minus xr minus y of point P. So xr is computed in previous round. So this is the xp and this is the yp here. And then by replacing this value, you see the y coordinate equals to minus 1.95. Okay, so let's review again quickly. You just draw a line that is passing through 2 point P and Q, and then the intersection point to find the intersection point between the line and the curve, and then reflect the point over the x-axis. So you're done. You find the addition of 2 points. So on the website, we have a tool that allows us to compute the addition. So here on the website, so over R, so we have point addition here. So you can change the value of P, change the value for coordinates of P and Q, and then the addition is computed. Like let's say the value of 2, I compute this 2, and then the value of y is updated automatically based on the formula of the elliptic here. So this is the point P here. So if I want to have point P with negative uh, coordinate of y, I can pick the negative value from here, right? So if I pick the negative value for P, can pick it here, and then I'm going to change the value of x of q, for instance, let's say -1, and then the value of y also is updated. If you want the negative value, you can pick the negative value. Okay, and now we see that in the website, again, we draw a line that is passing through P and Q, and then here, this is the intersection between the line and the curve, and then the reflection of this point over x-axis is finally the P plus Q point. And the value, the coordinate of P plus Q is computed also here. So the formula that is used backend for this website is actually the formula here in the slide that we discussed already, right? Okay, so now we want to discuss other forms of addition when P and Q are in different situations. For instance, the first one is when the point P and Q are the same. So in this form, the coordinates of P and the Q point, they are equal to each other. So this means that the 2 points are on each other on the curve. So in this situation, to find the addition of 2 points, which actually is the addition of P plus P, first you need to draw a line, but here you don't have two disjoint points to draw a line that is passing through 2 points. So here you have just 1 point. So the regulation says that first you need to draw a tangent line to the curve at point P. So now this dotted purple line is the tangent line that is pass through point P or Q. Both of them are the same. And then again in the intersection between the line and the curve, you need to reflect the intersection over the x-axis, and then you find the P plus Q, the addition of 2 points. So for this form, the formula to compute the slope is different from the previous formula. So now the formula is 3 times x of p squared plus a. So a is the value picked from here, right? So this was the a value in the elliptic curve, which is 1 in our curve. Over 2 times the y coordinate of p, and if you put the value here, the slope equals to 1.9, and then the formula to compute the x and y coordinate of point R, which is p plus q. So here R equals p plus q, which is this point, right? So this is p plus q or R. So the x coordinate of R is computed with the same formula, m or slope to the power of 2 minus x of p minus x of q, which is minus 1.4, and the y coordinate is 2.2 for this example. Okay, now we want to check the website to see how it works. So the website, you can pick 2 same value for x and y coordinate of p and q. So if I pick 2 here, I'm going to pick another 2 here. Okay, so let me check this for the positive value and this for 2. Okay, so now we see that the point P and Q are overlapping each other. So we draw a tangent line and then reflect the intersection point to reach P plus Q. So I'm going to change the value of X into 1 and then again 1. So then I see that the 2 point P and Q are overlap each other. So that the tangent line is intersect the curve here, and then the reflection computed P plus Q. And again here, this is the coordinates of the point P plus Q or R. Okay, so this was the second form of point P and Q when they are equal to each other. So now we want to discuss the third situation when the point P and Q they are at the same values for the X by negative value of Y. So here we see that the X coordinate of 2 points are equal to each other by the Y coordinate of 2 points are negative to each other. So in this situation, again, we draw a line that is passing through 2 points P and Q, but this vertical line never intersects the curve at all. So there is no intersection in this situation. And if you follow a formula to compute the slope, so you will see that the value here is 0, and then the slope also is infinite or infinite, right? So in this situation, we say that since the intersection is happening in the infinity, so then the addition of 2 point P and Q equals to infinity in this situation, right? Okay, so now let's see what we can see in the website. So in the website, if I have the value of P on 1 and 1.7, I'm going to have the value for Q1, but this one, a negative value. And now we see that, again, we have a vertical line. So the result, the addition, is a point at infinity. Okay, and now the final form, when the two points are simultaneously equal to each other, and also the line that is passing through 2 points is a vertical one. So again here the x value, the x coordinate of 2 points are equal to each other, and the y coordinate of 2 points are equal to each other. But when you are drawing a tangent line, this tangent line doesn't intersect the curve at all. So again, the formula to compute the slope equals to infinity. And again, we say that the addition of 2 points on this curve is at infinity. So let's see this situation on the website. So here you want to pick the value of y. Here I'm going to find the point here. So I don't know what is the exact value of y, but I know that the value of what exact value of x, but I know the value of y equals to here equals to 0, right? So then I'm going to click here, and it allows me to enter the value of y instead of entering the value of x. So I click here, and it says that, okay, first you can enter the value of y, and if I enter 0, I will reach to this value, and automatically the value of x equals to minus 2.28, right? For the point Q, I'm going to enter the value of y. So I'm going to insert the value of 0 here, and it automatically set the value of x equals to minus 2.28, right? So here we have a tangent line that does not intersect the curve. So you remember that when we had the value of 2.x P and Q on a vertical line. So the vertical line never intersect the curve, but it was not a tangent line. But here it is a tangent line that does not intersect the curve, and again the addition equals infinity, right? So we discussed 4 different kinds of situation when P and Q might happen. And now this is done for the elliptic curve point addition. Now we want to discuss about scalar multiplication. And scalar multiplication means the n, which is a scalar value times of a p, and p is a point on the curve. So n times of p equals to adding p n times to each other. So we doesn't have point multiplication. So we already discussed point addition, but we doesn't have point multiplication. Maybe we have, but at least in this lecture, we do not discuss it. So scalar multiplication is kind of the addition, right? Addition of one point to each other multiple times. So n times means that p plus p multiple times, and now we want to overview the concept with an example. So the value of x and p coordinates for x and y coordinates for point p are set here, -1 and 2.65, and this is the point p on the curve. Now we want to compute 2p, and 2p equals p plus p, right? So computing p plus p from previous discussion, to compute p plus p, we need to draw a line that is tangent to curve, the elliptic curve, and then find the intersection and reflect the intersection point over the x-axis, and then find the final result for the addition. So based on that method, now we can find the 0.22p, which is p plus p here at this location. Okay, now we want to compute 3p, which is p plus 2p. So we have 2 points p and 2p. To compute the addition, remember that we need to draw a line that is passing through 2 points, and then find the intersection, and then reflect the intersection over the x-axis, and then we can find the addition, which is 3 times of p. Okay, 4 times of p means that p plus 3p, and to compute p plus 3p, again, you need to draw a line that intersects from p and 3p, find the intersection, and then reflect over the x-axis, and then you'll see the 4 times of p here at this point. Okay, on the website, we have the scalar multiplication also. So let's see the website. So this was the addition, and this is the scalar multiplication. So the value of A and B is set here. I'm going to change the value of A and B into 1 and 9, which is the curve that we discussed in the PowerPoint, and you will see more this curve in next lectures. So now we want to compute scalar multiplication of n times for the point P and Q. So I'm gonna enter like maybe 2 here, and then the value of 2p, which is p plus p, equals to minus 1.78 and 1.27. So you can increase the value of n like maybe 5. Okay, you don't see the result because the range is not enough. So you increase the range, and if you increase the range into 20, you will see 5 times of p here. Or maybe you can add like maybe 4 times of p, and then it's not in the range, so I'm going to change and increase, and it's not enough yet. Yeah, okay. So 4 times of p is shown here. Okay, so this is everything about the elliptic curve, and also addition of 2 points and scalar multiplication. Now we want to switch from the continuous form into discrete form, and then use the discrete form version for cryptography. To switch to discrete form, we want to discuss elliptic curve over a field f sub p, and we will work with f sub 101 as an example. So you remember in previous lecture we discussed f of f sub 101, which is a set start from 0 until 100. And now we want to see what is the meaning of elliptic curve over such a field. Okay, so we say that if you put the value from the field, which starts from 0 till 100, and then pick the value from this set and replace for the x and the y. For instance, maybe you pick 0 for x and 1 for y. So if you put this value in the formula, and then y to the power of 2 equals to x to the power of 3 plus x plus 9 in mod 101, so then you say that, okay, this chosen pair is accepted in our set. Okay, let's overview with an example. We want to pick 0 and 0. Both value for x and y is replaced by 0. And so if you replace 0 here in this formula and 0 here and 0, so you will have 0 to the power of 2 equals to 0 minus 0 to the power of 3 equals to 0 minus 0, and it's finally equals to minus 9. And then you need to compute it in mod 101 because our discussion is in the field of f sub 101. And if you compute this value, you see that the result is not equals to 0. To compute mod, you remember that we had a tool in our website. You can use the website here in the modular arithmetic. Here you put 101 here, and then what was the value here? Yeah, minus 9. And you will see that minus 9 mod 101 equals to 92. Okay, so since the value does not satisfy this equation, so then we say that the point 0 and 0 is not accepted. Okay, so let's review another point. Again, we want to choose 0 for x and 3 for y. So if you put this value in the formula, you will see that 3 to the power of 2 minus 0 to the power of 3 minus 0 minus 9. This is 9, and 9 minus 9 equals to 0. So then this check is approved. So point 0 and 3 is a valid point. So, so if we check different points given from the field F sub 101, you will see that these are blue circles are showing the points that are accepted because they are satisfying this condition, right? So the point 0 and 3 is approved already, and this is shown we have shown the point here. So let's see another point. So we want to see another point here, and the point is 25 and 2. So this is a point here, and we want to ensure that this point also is satisfying this formula. So let's put 25 instead of y, and then put 2 instead of 0, and then do the computation. So you will see that the final computation is negative 15,655. And if you compute this value in mod 101, you will see that the result equals to 0. And since the result equals to 0, this check is passed. So then this point is accepted. So if you check for all of this point, you will see that this equation is passed. So that's the reason we draw this circles here. For instance, if you pick a value from here, like maybe like here, 50, 75, and 25, and put this value in the formula, you will see that the check would not be approved, right? So then this point is not accepted. So we have a curve and we have a field. So from combination of a curve and a field, we will have a set of discrete points that we later use for cryptography. Okay, so let's see the website. So in the website, in the elliptic curve cryptography, when you click on over f of p, you can pick different value for the parameters of the curve, and also for the to determine the f sub p, which is the fit. So for our computation, we picked 101 as the prime value, and the f sub 101, and 9 as the b value for the curve, and 1 as the a value for the curve. And then the figure here is automatically compute to find the valid points. So let's see other values for the p, for instance, maybe 19. So if you put 19, so then we see that the valid points are computed here. So let's enter another big value, like maybe 3, 5, 7, or maybe it is not prime. But anyway, so we see that by increasing the value of the P, we have a bigger field. So we have bigger options, and then we have bigger valid points. Okay. Okay, so now we want to, so here we see that for this curve and the determined field, we have 119 points. So we discussed that when we increase the value of P here. So then we have more extra points. So other than the points here that you see in this figure, there is a point is infinity that is considered also as this set. So maybe I add infinity here to show that the set consists of these blue circles and also a point is infinity. Okay, now we want to discuss point addition and scalar multiplication. The previous discussion on the continuous form elliptic curve, here on this discrete form, to see how the point addition here means. So we have 2 points here picked from the valid points. X of p equals to 7 and y of p equals to 37, which is this point, and the point of Q 23 and 68, which is this point. So we don't have any continuous form here, so we don't have any line that is passing through 2 points P and Q and then intersection and reflection, blah, blah. But we can follow the formula that's already had in the continuous form. So the formula mentioned that first you need to compute the slope of line that is passing through 2 points. We don't have any line that pass through 2 points here, but we use the same formula to compute the slope. Y of q minus y of p over x of q minus x of p. And if you replace the value, you will reach to this one. And now we are in the discrete form and modular arithmetic. And from discussion in lecture 2, you remember that we cannot have any float values, and then we need to compute the inverse of 16, right? We discussed in lecture 2 how to compute the inverse of a value in modular arithmetic. So using the website or using the manual computation, you can see that the inverse of 16 in mod 101 equals to 19. Okay, so let's check in the website to ensure that this value is computed correctly. So in the website, in discussion of lecture 2, modular arithmetic, we had modular inverse. So the prime value or the P equals to 101, and we want to compute the inverse of 16. It is equals to 19, right? So the inverse of 16 equals to 19. And then by replacing the 19, we have 589. And again, if you compute using the website or manual, 589 equals to 84 in mod 101, right? Because all of the computation is computed is mod 101. Okay, we follow the formula, the Price formula again to compute x of r, which is x of p plus q. And the formula says that finally the x value would be 57 and the y coordinate based on the formula equals to 5. And if you find the point 57 and find, it is here, which is p plus q, is shown in the figure, right? Okay, so we don't have any line here. We don't have any tangent line or a line that is passing through 2 points, but we follow the same formula. So let's see the website and check to use the website for other examples. So in f of p, so I'm going to define the curve here. So it is set already. So this is the list of points here also. Okay, so here, here we have the list of points, uh, the list of points that are shown in the figure, and then we can compute the point addition here. So, yeah, we have the list of points. Here, maybe I'm gonna add this point, 65 and 79. And with another point, 99 and 91. So addition of these 2 points equals to 21 and 91. So we can see the points here. So if you enter a point that is not valid, like maybe 64, so the point is not valid, right? So we see this error here. Okay, using this website, you can do some examples by yourself and then get the idea of point addition more. Okay, after point addition, we want to discuss the scalar multiplication for the points here. So we already discussed that scalar multiplication is another form of addition of a point to itself multiple times. So let's do it using the website for the scalar multiplication here. So for instance, you wanna enter a point like maybe 0 and 3, 0 and 3. If you put 0 and 3, 3 times of this point here equals to 66 and 23. So again, this means that adding the point 0 and 3 to itself 3 times, you can compute the values using the formula, or you can use this tool to see the results in the figure. Or maybe you want to add the value of like maybe 44 times, or not, this is 0, this is 3, so this is the value, and 44 times of the point equals to 8 and 23, or 99 equals to 91 and 98, right? Okay. Now we want to discuss another concept, group G1. So the question here is that what is the benefit of defining elliptic curve and then the continuous form and discrete form of the elliptic curve? Now we want to discuss to see that, yeah, we want to generate a group using the elliptic curve and the field F sub 101. And later you will see that what's the benefit of such a group. Okay, so you remember from the lecture 3, the group is set of elements and a binary operation between those elements that satisfy 4 properties, right? So now we want to say that the group that already generated uh, is a group, right? So group G1 is a group of points that is generated from the elliptic curve that we already chosen over a finite field F sub 101. So this is the set of elements, and also we had a point in infinity, and we want to see that if this is a group or not, right? So the operation also here is addition, right? So because we already discussed addition between 2 points or addition between 2 elements of such a group. So let's see if the group of G1 with the addition operation is a group or not. So the first property says that if you pick 2 elements or 2 points from this group and then add them to each other, the result should be another element or another point in this group, right? Okay, so If you use the website and use the addition tool, you will see that if you add any two elements like these two elements, so the result would be another point, like maybe this one or this one, right? You cannot find 2 points that addition is not a point in this set. Okay, so then you can check and you will see that the first property is satisfied. So the other property is seeking identity element, and it says that if you add an element by itself, the result should be the same and doesn't change. And such an element is infinite. The infinite uh, element of the group, so this one, this is the identity element in the group of elliptic curve because addition of each point with uh, infinite equals to the uh, uh, to that point. So the third property is the inverse element, and it says that you need to pick, you need to have a another point in the group that when you add with the original point, the result should be equals to infinite. For any uh, element, you need to have such such inverse. So let's check in the website to see that if we can find uh, the inverse of an element here or not. Okay. So for instance, let's say 0 and 3, and the other is 0 and maybe 97 or something like that. 0 and 3, and another 0 and 97. Now 98, 98. So this one. So for the point 0 and 3, the inverse is 0 as and 98 because 0 and 3 plus 0 and 98 equals to infinite. So then we could find the inverse of point P here. So if you check and see this figure, you see that any element is in this figure has a reflection point over a line, right? Let's go back to the, yeah, let's go back to the slide here. If I draw a line here on almost 50, you see that each element in this group has a reflection over this line, right? For this one, for instance, we have this reflection. For this one, we have this reflection, or for this one, we have this reflection. If you use the website or the formula and then compute addition of each of these two reflection points, like these two or these two or these two, you will see the result equals to infinite. Like in our example, we already add these two values to each other, and we notice that the result of addition is infinite, which is the identity. So then we say that, okay, there is an inverse element in the set. For instance, if A is this one, so then this one would be the inverse of A. So the inverse of each point in this set is a reflection of the point over the draw line. Okay, the third property is satisfied, and for the fourth property also, if you check using the website, for instance, if you pick this point as A, and then this one as B, and then this one as C, and then compute the addition of 2 points A and B first, and then add by C. So you will see that the result equals to if you add 2 point B and C and then add with A. So the property, the final property is accepted also. And now we can say that, okay, so now we have a group, and we call it group of G1 here in this lecture, because later we need this G1 for our discussion. Later we will discuss and introduce another G, which is G2. Yeah, and if you remember the discussion about the group, so we had a discussion of generator. Any group has a generator, right? A generator was an element that you could repeatedly combine that element to itself and then generate other points in the group. And also, we discussed that there is not an easy to follow algorithm to compute generators. Sometimes it's just a trial algorithm. But anyway, so for this group, we want to say that the generator is 0.4 and 28, right? And the 4 point and 28, I don't know, maybe the point is here. Yeah, maybe this is the point. So if you multiply this generator to itself n times, you should be able to generate all of these elements, other elements. So let's check in the website to see how it works, right? So we want to check using the scalar multiplication. So this is the curve, and we discussed this. The generator is 4 and 28. So this is the generator 4 and 28. Okay, if I put 2, I will generate 48 and 85, right? If I put 3, I generate 50 and 18. If I put 4, I generate 27, 78 points. So by different value of n, I should be able, all of the points in this figure and even the point in the infinity, and then I can see that, oh, correct, this is the generator of this group. Okay, now we want to discuss Lagrange problem, discrete Lagrange problem, which is a difficult problem that we use in cryptography. So the problem says that if you have 2 points on the elliptic curve, like P and Q, in a way that Q is n times of P. So if P is a large prime value, so for our example, the value of P is 101, right? So 101 is not a big value, but to understand, we discuss with a small value. So for a big value of prime, and n is a random integer, if the value of P and Q are known and public, so given the value of P and Q, and by this condition, if somebody knows Q and P, it's not easy to compute the value or guess the value of n. And this is extremely difficult problem. Okay, with our current computation power, we cannot solve this problem. Okay, so let's discuss in the website. So this means that in our website, if I have, like, let's say the value of P equals to 4 and 28, or maybe a different value like 25 and like maybe 3. No, this is 4. Let me find another one. 33 and 86. 86. So I'm going to consider this as point Q, and then I'm going to give you the value of 33 and 86, and also 89, 0 and 89. So finding n, which is equals to 4, is impossible for you by knowing just the value of point P and the results of n times of point P, unless the value of prime is small, right? In practice, we have so big values for prime, and for those very big values, you will have billions of points here in the group, and then guessing the value of n is impossible. And this is called the discrete Lagrange problem in elliptic curve. And later again, you will see and hear more about this problem. Okay, so let's review quickly again. We discussed elliptic curve, and then using the field defined in lecture 3, we could define and generate a group by checking that if the elements from the field are satisfying this condition or not. Now, you remember that in previous lecture, other than the field f sub 101, we discussed another field, which was f sub 100 1 s squared, that was generated from field f sub 101, right? And irreducible polynomial. So we discussed these two fields in previous lecture. Now we want to follow the same method to generate another group using the extension field. So then we say that the elliptic curve over the extension field f sub p to p squared. So now again we have another condition that should be passed by picking the value from the elements of f sub 101 squared, and then replace it by x and y, and then check that if y to the power of 2 minus x to the power of 3 minus x minus 9 mod 101 equals to 0 or not. So for instance, we want to check to see that if this point is satisfying this equality or not. So we want to put this value for x and this value for y, and both of these two values are picked from this set, right? So one value is chosen for x, the other one for the y, and then we want to compute y to the power of 2. So y to the power of 2 equals to this one to the power of 2, and then you compute this and compute all of the values in mod 101. And also you need to replace the value of I squared, right? So we discussed this multiplication in previous lecture, and also we have uh, some tool in our website that allows to compute multiplication in extension field, right? So we need to replace the value of I to the power of 2 with this value, and then finally compute all of the values in mod 101, and this is the value of y squared. So the value of x squared equals to 6 plus 5i using the same method or using the website. So let's see our website. So in our website, we had the extension field computation. We had the exponentiation, right? So the exponentiation is uh, 3, and then the value of x equals to 89 and 51. 89 and 51. And if you compute these values. So it will be equals to 6 plus 5i, right? Using the website, we can compute this value, and then by adding x to the power of 3 plus x, we have 95 plus 56i, and then plus 9 equals to 3 plus 56i, which is equals to the value of y to the power of 2, and then y to the power of 2 minus this value equals to 0. So then this point is satisfying the equality, right? Equality test. So then we say that, okay, this is an accepted element uh, to our new group. So if you check other elements from the extension field, you finally you can check using the website or the manual computation to see that if an element is accepted or not. So let's say the website. So here in our website, on the elliptic curve, and then over the extension field. So this is the curve is already defined, and the values for the I to the power of 2, and then we want to check to see that if a point is an accepted element or not. For instance, if I put 3 and then 5 and then 2 and like maybe 9, so this is not an acceptable element, right? So, but if you check other values, so then you can see that the list of accepted point is so big, and for these values and the Veil algorithm that we will discuss later, around 10,000 points are accepted. So you remember that over F sub P, we had around 100 points, but here we have around 10,000 points in the extension field, right? So we have a big list of those values, the extension field, and then we didn't list all of those accepted values that satisfy this formula, but because the list is more than 10,000, but at least this is some examples of the elements that satisfy this formula, right? Okay, so now we want to discuss the addition over this extension field. So the term again is y to the power of 2 equals to x to the power of 3 plus x plus 9. The extension field is f sub 101 squared, and the irreducible polynomial is x to the power of 2 plus 97x plus 2, which concludes I squared equals to 99 plus 4i. So the addition of two elements to each other, so it says, like, for instance, we want to add 89 plus 51i and 63 plus 93i. So this is point P. This is not a point. This is element P plus 0 plus 0i and 3 plus 0i, and this is element Q, right? So we want to add these two values to each other. So you will add the x values to each other and y values to each other, and then you compute the mod 101, and though the final value would be this, right? So Okay, so then in the website we have the addition of 2 points here. So if you put the values that are not valid, so you will see that the element P is not on the curve, right? Maybe you want to pick the value from the list here. For instance, 9. I'm gonna add 9 for the real, and then 0 here, and then 79 and 11. So the other point is 3 and 0, which is this one. So addition of these two elements equals to this element, right? So you can use from this tool to compute this addition. And then we want to discuss the scalar multiplication, which is addition of one element to itself multiple times, right? For instance, we want to uh, add this element to itself because it is 2 times here. So 89 plus 51i, sorry, and 63 plus 93i plus itself, right? So the result would be this one. And you can increase this 2 by 3, 4, and blah, blah, or use the website tool. So here in the scalar multiplication, you can increase the value of n to compute 3 times of the elements. And now, since we have a set of values and an operation of addition, we want to see that if this set is also considered as a group or not. So it should satisfy this list of four property. So now we want to call it as group two. So the group two is a group of element that is generated by define elliptic curve over the extension field. So sorry, it should be f sub p squared, right? So this is f sub p squared. So this is not the total list. The list is so big, more than 10,000 elements, and it is generated by this curve and over this uh, uh, extension field. And then if you check the four property, you will see that the four property are satisfied. If you pick any two elements from this set, you will see the result is another element that maybe it is not listed here, but in the website we also have tool that allows you to see that if the element is a accepted element or not, right? So you can add all of these two values to each other and check and ensure that the result is an element in the group. So then we have another infinite value that is work as identity elements. So then we have inverse element also, and the associativity property is satisfied. So then this is accepted group, and we call it as group two. So this should be also two. The set of G2 is an additive group. And now, like previous discussion, when we have a group, we have a generator, and our generator for this group is this one, 89 plus 51i and 63 plus 93. So this means that if you add this G multiple times to each other, you should be able to generate all of these more than 10,000 elements by just picking different values for n. Okay, now we have two groups. Let's overview quickly again. Group of G1, which is generated by the elliptic curve y to the power of 3 equals to x to the power of 3 plus x plus 9 over the field f sub 101, and the generator of this group is 4 and 28. So maybe this one. This is the generator. For the other group of G2 is a group generated by the same curve, but on the extension field, and the generator is 89 plus 51i and 63 plus 93i. So yeah, the goal of this discussion was to just generating these two groups. So in the next lecture, you will see that how this two group allows us to define the concept of pairing, and then pairing is a uh, is a tool that we needed to design Growth 60. Okay, so yeah, for our discussion, we use this elliptic curve y to the power of 2 equals to x to the power of 3 uh, plus x plus 9, and this very small field with a small value for the prime, which is 101. But in practice, we have so big value for the prime, right? For instance, in the Bitcoin and Ethereum, we are using from this formula for the elliptic curve, y to the power of 2 equals to x to the power of 3 plus 7. So this means that b equals to 7 and a equals to 0 for the Bitcoin. And the value of p is so big, right? In our computation, the value of p equals very small value, 101, but in Bitcoin and Ethereum curve, it is so big. For Apple, TLS and government standard, we are using another form of elliptic curve with another big value for the prime. WhatsApp and Signal, they are using a big value for the prime, and this figure for the elliptic curve, and then other kind of. Thank you for this lecture.